Welcome to this explainer. Okay, imagine standing right at the precipice of a completely new era in astronomy, staring down the barrel of the Nancy Grace Roman Space Telescope. We're preparing for a mission of just unprecedented scale. It's this panoramic window into the universe that's going to map the cosmos thousands of times faster than Hubble. But with that incredible, futuristic capability comes a very modern, very massive logistical challenge. So think of this as your official mission briefing for the infrastructure that's going to make all this science actually possible.
Now, I want you to really think about this for a second. How do we actually handle petabytes of space data? I mean, when Roman finally opens its eyes, the sheer volume of data streaming back to Earth is going to be absolutely astronomical, pun intended, of course. For any individual researcher just sitting at their laptop, prepping for Cycle 1 proposals, trying to download and process that absolute fire hose of raw pixels, it would be completely overwhelming. It's way too much data, it's coming in too fast, and the processing required is just too intense. So how does the community actually use it?
Okay, let's dive right into this, because there's a massive distinction we need to clear up right away. On the left, we have doing science, and that is your job. That's what the community researchers will do. But on the right side, we have enabling science. NASA has funded 5 huge, highly specialized groups called the Project Infrastructure Teams, or PITs. These teams aren't hoarding all the data to write the science papers themselves. No, their entire mandate is to build the Pixel-to-Cosmology framework that empowers you to do the science.
So here is our blueprint for today's explainer. First, the Pixel-to-Cosmology framework. Then we'll meet the 5 PITs. After that, we're looking at Rapid's prompt public alerts, ARGis's occurrence rate pipelines, and HLIS's weak lensing shear. And finally, we'll wrap up with the Roman research nexus.
All right, Section 1, the Pixel-to-Cosmology framework.
Before we get into the individual tools, we really need to understand the foundational purpose of Roman's infrastructure, and I literally cannot emphasize this enough. The PITs are the architects here. When you look at raw telescope data, your level 1 and level 2 files, it's just full of instrumental noise, detector artifacts, and super complex astronomical anomalies. The PITs are doing all the heavy lifting to bridge that massive gap between raw pixels and actual cosmology. They're building the software, running the massive supercomputer simulations, and laying down the data pipelines so that when you finally sit down to write your Cycle 1 proposals, you have clean, calibrated, ready-to-use tools right at your fingertips.
Moving right along to Section 2, let's meet the 5 PITs. So NASA officially selected these 5 project infrastructure teams. We've got Rapid, ARGis, HLIS, the Supernova Cosmology team, and the Galaxy Redshift Survey team. Each one of these is made up of dozens of leading scientists and software engineers. And while all 5 are doing just absolutely incredible work for the community, today's deep dive is going to focus specifically on the critical deliverables coming from Rapid, ARGis, and HLIS.
Which brings us to Section 3, Rapid, and their prompt public alerts.
Now, what's really interesting about this is the low latency timeline. Rapid stands for Roman alerts promptly from image differencing. And as we all know, time is of the essence when the universe changes. Check out. Step 1. The telescope takes an image with its wide-field instrument, beams it back to Earth, and within 48 hours, it's calibrated. Step 2 is where the magic really happens. Within just 1 hour of receiving those calibrated images, the Rapid pipeline performs image differencing and spits out a prompt public alert stream. So if a star explodes, if an asteroid flies by, if literally anything flickers in the deep dark of space, the community is going to be notified incredibly fast. You are getting instant alerts for transients and variables.
But wait, Rapid doesn't just stop at a quick alert. They're also delivering candidate light curves over the time domain, giving you the historical brightness of these objects. Plus, they're providing a public forced photometry tool, which lets you instantly measure the brightness at any specific coordinate. And guess what? Their pipeline code is totally public right now on GitHub. This gives the entire community the extra tools they need to investigate multi-messenger science and immediately jump on sudden astronomical events without having to write all that underlying software themselves.
Next up, Section 4, ARGis and their occurrence rate pipelines.
Okay, so this team handles the infrastructure for the Exoplanet Hunting Galactic Bulge Time Domain Survey. And here's where things get super fascinating. Let's break down this deliverable, because the absolute main responsibility of the ARG PIT is building the occurrence rate pipeline. Just imagine a software tool that doesn't just say, hey, we found a planet, but systematically outputs the actual number of planets as a function of their mass, their semi-major axis, how far they orbit from their star, and the mass of the host star itself.
We're talking about demographics on a galactic scale, turning individual detections into a massive statistical understanding of how common different planetary systems really are.
And the best part? ARGis isn't going to make you wait until the end of the entire multi-year mission to figure out how well things are working. They're also providing value-added tools like first-look efficiency maps. After just the first season of observing, these maps are going to help researchers calibrate the survey's progress. This is huge, guys, because it allows you to extract cold exoplanet demographics super efficiently, making sure your science is immediately on track.
All right, Section 5, HLIS and weak lensing shear.
So, to study the dark universe, the High-Latitude Imaging Survey focuses heavily on gravitational lensing. And to do that, 40! Just take a look at that number. In the world of weak gravitational lensing, where we're trying to measure those tiny, almost imperceptible distortions of background galaxies caused by invisible dark matter, density is literally everything. For the Roman High-Latitude Wide Area Survey, we're expecting an effective source density of 40 galaxies per square arc minute. That is a staggering amount of data to process, and measuring the weak lensing shear, the shape of every single one of those galaxies, requires absolutely immaculate precision.
To handle that kind of mind-boggling density, the HLIS team is building some absolute workhorse tools. They're providing highly complex simulated data so you can actually test your code right now. They're building systematics mitigation tools to perfectly remove tiny instrumental errors from those galaxy shapes, and they handle both the imaging and the GRISM spectroscopy components, splitting the starlight to see its chemical makeup, across a massive 2,400 square degree wide area survey. This basically ensures that when you want to make large-scale clustering measurements of the universe, you've got the impeccably clean catalogs you actually need.
Finally, Section 6, the Roman Research Nexus.
We've seen all these incredible tools being built, but where will they actually live? Well, this brilliantly illustrates exactly how all of this comes together. Look at this incredible flow of data. It's beamed via Ka-band telemetry from the spacecraft, down to our ground stations, and right into the Daphne cloud. From there, it flows seamlessly into the Science Operations Center at STSCI and the Science Support Center at IPAC, where the pipelines we literally just talked about process it from raw levels all the way up to high-level catalogs. And ultimately, those refined, beautiful data products flow directly to the community.
But how do you, sitting at your desk, actually access it? Enter the Roman Research Nexus. This is a totally cloud-based collaborative computing environment. Remember my question at the very beginning about handling petabytes of data? Well, the Nexus removes that burden entirely. There is no downloading petabytes to your laptop. You don't have to navigate super complex software installations or beg your department for a supercomputer. All of the PIT tools, the pipelines, the simulations, and the data itself are preloaded right here in this cloud environment, completely ready for you and your collaborators to access and analyze together in real time.
And I want to end on this incredibly empowering quote. All Roman data will be public with no proprietary period. I mean, the absolute second those pipelines finish processing the pixels, the data is yours. The prompt alert streams from Rapid, the occurrence rate pipelines from ARGis, the weak lensing shear estimates from HLIS, they are all yours. So, the only question left for you is, what groundbreaking, universe-altering discovery are you going to propose for your Cycle 1 observations? Thanks so much for joining me on this explainer, and honestly, I cannot wait to see what you find out there.